Launching it. All right, welcome to today's webinar on Alaska storminess in a changing environment that is presented by Rick Thoman of our Alaska Center for Climate Assessment and Preparedness at the International Arctic Research Center at the University of Alaska Fairbanks. He's been a climate and weather professional for more than 40 years, including 30 years with the National Weather Service in the Alaska region. And he has a great depth of expertise that he is sharing with us today. And on that note, I will turn it over to Rick. He has requested that questions be saved for the end. So if people want to post questions as they go along in either the chat or the Q&A options, I will pass them on to Rick at the end.
All right, great. Thanks very much for the introduction, Vicki. And hi, everyone. And thanks for taking time out of your Wednesday morning to join in. So today I'm going to be talking about storminess in Alaska in a changing environment. And so you should feel pretty special today. This is a question: how is storminess changing in Alaska? I've been asked this, many times in the last 20 years, and I've never had a good answer for it. But just recently, we have a new database that allows us to assess this. So this is the premier edition of Rick's Changing Storminess in Alaska presentation. So questions or comments that will help improve this will be great. But this is very much cutting edge information for Alaska. So let's see if we can make the technology work. Okay, so going to start out here. This is our relatively straightforward agenda today. We're going to start out, though, with what seems like maybe an unnecessary question, but actually a complex question. What do we mean when we say storminess? And what are the perspectives on storminess? This actually is important to understand and to get a handle on to really assess if and how storminess is changing. And then we'll end up this presentation with the future, just a little bit on the future prospects for storms for Alaska, however we define storms. Oops. Okay, so what is a storm or storminess? Does a storm require that there be some, a lot of precipitation? If you're in a tundra area, you are familiar with ground blizzards. Sky's completely clear, sun shining, and you can't see 50 feet in front of you because of the strong winds and blowing snow. Does that count as a storm? Does a storm require strong winds? If you're in Valdez and you get 4 feet of snow in 2 days and the winds calm the whole time, does that count as a storm? If a storm requires strong winds, do they have to be from a particular direction? And does a storm need to last a minimum amount of time? For our purposes, does a thunderstorm count as a storm? Does a 3-day blizzard count as 1 storm, 2 storms, 3 storms? Those kinds of questions are all things that actually come up. These are not hypotheticals. These are all things that people can have different viewpoints on. And of course, as almost everything with climate and environment in Alaska, because Alaska is so big and such diverse environments, are the answers to these questions regionally dependent? So what constitutes a storm in the interior, is that different than what constitutes a storm in the Aleutians? So what's a storm or storminess? So what's first, or at least second thing I think to do? Okay, let's go look up some reference definitions. And so here's what we get. This is just a handful I picked off the internet. So from the New Oxford Dictionary, a storm is a violent disturbance of the atmosphere with strong winds, usually rain, thunder, lightning, or snow. So by that dictionary definition, strong winds would be a requirement. Other stuff might come along with it. Okay, we can work with that. That's something we could evaluate. Now, from Wiki, uh, had this definition, which to me is completely unhelpful. A storm, a disturbed state of the natural environment or the atmosphere. What the heck is a disturbed state? How would I know a disturbed state if I see it? Um, and the Glossary of Meteorology, a long-standing publication by the American Meteorological Society, has one of the definitions of storm, a transient occurrence. So that sounds like short term, identified by its most destructive or spectacular aspect. Okay, well, so that covers things like windstorm or thunderstorm or snowstorm, but doesn't really get at what constitutes a storm. So I didn't, with at least the first one we could evaluate, we could talk about. I'm not sure the other two are really helpful in helping me at least understand what is a storm or storminess. Now, how about the Alaska perspective, which is really all that we care about? So when we talk about storms in Alaska, we are usually thinking about low pressure systems, with the exception of thunderstorms, which I'm not going to deal with in this presentation. Here, we're talking about larger scale weather features. So storms, low pressures, L's on a weather map. Storms, lows, pressures, are almost always major players in coastal floods. They're also important, or the driver of most, but not all, heavy rain and snows. The big exception to that is across interior Alaska, where very heavy rain and snow can occur with no low pressure system anywhere within hundreds of miles. Strong winds can be associated with low pressure systems, but they don't have to be. And some of the exceptions to all of this are listed there. So the interior rain and snows, mountain modulated windstorms, Taku winds in southeast, Matanuska winds blowing down the Matanuska Valley. Those are generally actually driven by high pressure, not low pressure. And of course, similarly, with clear sky ground blizzards, primarily in tundra areas, they might be associated with low pressure, more often with high pressure, but not normally driven by low pressure systems. So that's one perspective from the Alaska side of the house. Lows are a major player. The coastal flood is really the big thing where you don't have a low, you don't have coastal floods. So how about the Western science perspective? So here we have kind of the meteorology side of the house. So the graphic there just shows a weather map. This is actually a forecast for today, made a couple of days ago when I put this slide together. And you can see all kinds of L's and H's on that map, high and low pressure systems. So, and from the meteorology perspective, a storm is basically an L on that map. Area where the air flow is counterclockwise in the northern hemisphere, clockwise in the southern hemisphere, so that when you face into the wind, so the wind's blowing right in your face, you're going to have lower pressure to your right and higher pressure to your left. Now, that works really well if you're on a small island in the ocean or on a ship in the ocean. Land greatly disturbs that simple pattern. Now, pressure in a low, the pressure is lower towards the center of the circulation. And when meteorologists use the word storm, again, that's a synonym, it's a jargon synonym for an L on the weather map, and doesn't imply anything about intensity or impacts. So if you sit in on a weather briefing, you might hear, a weak storm will move through the Aleutians and into the southern Bering Sea. Obviously that weak implies something about the intensity. But it doesn't, just because a storm will move into the southern, across the Aleutians into the southern Bering Sea, doesn't tell us really anything about its depth, intensity, potential for impacts, expected impacts. Now, let's, let's see. There we go. So hopefully you can see the weather map now looping. So this is a couple day loop of a forecast here. It's every 3 hours. Each frame is every 3 hours. And you can see the L's move around. I'll call your attention. So Alaska's kind of, this is centered on the North Pole. Alaska's kind of there at about 8 o'clock there. And you'll notice as this loops through, you'll see there a low off the southern panhandle, and all of a sudden it jumps and gets squished. You can see the high pressures also moving around, some of them. Some of the highs and the lows aren't moving very much. When we talk about highs or low pressures, but especially with low pressure, the intensity or the strength of the low is related to the lowest pressure. Now, that's typically measured in millibars, is what plotted here, or inches of mercury. And that's kind of interesting because while we obviously have a good sense of what winds are, pressure is one of those things. Most people, of course, are insensitive to pressure, whether it's high or low pressure. Most people, you don't walk out and say to your buddy, "Oh, today's a high pressure day. I can feel it." Most people can't tell the difference in atmospheric pressure, which varies, about 15% in any given place over the course of the year. So intensity related to strength. The more intense, the stronger the wind. That's almost by definition. Now, storms, low pressure systems, and high pressure systems, they all go through a life cycle, development, intensification, and decay. On small scales, that can happen in the space of a couple of hours, a thunderstorm. For instance, at the larger scale, the scale we're interested in here today, that typically 4 to 8 days from formation to decay. Some storms, though, are very long-lived and can last a couple of weeks. Now, one of the most important jobs of the weather forecast is to track the movement of low pressure systems, of these storms. And storms are how they move are mostly controlled by what's happening with the winds aloft, say 15 to 30,000 feet in the atmosphere. Those are the winds that are going to move the storm around. And that includes when the winds at that altitude are light or variable, the storm may not move very much. Now, another important factor, and this is really important for Alaska, is storms interacting with the land. In the loop there, I mentioned that low off of southern southeast Alaska early in the loop basically runs into the big coastal mountains and just is shredded by it. And that is a important factor in storm evolution for Alaska. It's also, of course, an issue farther south. Anywhere where you have big terrain, that this is going to be an issue. And where the big terrain is near the coast, like it is in southeast, south central Alaska, that this has a major impact on how storms move, where they move, and how they dissipate. Things are much cleaner over the ocean. Of course, 70% of the Earth's surface is ocean. So we know how things happen quite well over the oceans, but the interactions with land are a big complicating factor. So where storms move is a major determinant of the impacts it's going to have on any particular stretch of coastline and later inland areas. So what the graphic here plots, all the storms identified in our new database here from January 1990 The colors here I just split up into early January and late January just to make it a little easier to look at. And the size of the dot is proportional to the intensity of the storm. So the bigger circles are more intense. The little tiny ones are quite weak storms. And then the numbers there are just in this database, every storm gets a unique identifier. And so this just makes it easy to track here. So um, the aspect of the coast, of course, determines the threat direction. So places like, let's say, the southern Seward Peninsula coast. So this would be Nome, Gullivan. These areas are on south-facing coasts. And so storms that move to the west, to their west, remember in the northern hemisphere, the winds around low pressure are rotating counterclockwise. So a storm to the west, remember, stand with your facing into the wind, and the lower pressure will be on your left-hand side. Those are the winds. That's the storms to the west are what's going to be southerly or southeasterly or southwesterly winds pushing that ocean water into the coast. The exact same storm at a place, say, like Shishmaref on the northern Seward Peninsula coast would have very different impacts. And of course, winds are not static as storms move along, and the change in the timing of the wind direction are all very important for impacts for coastal areas. And that track is going to determine where the maximum rise in those ocean levels are going to occur. So this is all a really important, this is why we track this so hard. There's all kinds of interesting things in this graphic. I'll call your attention to the storm that actually has the biggest circles here. This is storm number 333, if you can see that. This storm actually originated in middle of January south of Japan, moved to the northwest there, and you can see it there. It moves up to outer Bristol Bay and then actually does a loop-de-loop there between St. Matthew Island and Nunivak Island. It does a loop and actually moves back inland before it into the YK Delta there, or the Kuskokwim Delta, before it dissipates. Another loop there is storm number 41 in the purple in the southwest Bering Sea. That actually makes a loop there and winds up moving into the northern Kamchatka Peninsula there. So a lot of interesting info, and all of this is important to impacts. Up northeast of Alaska there, storm number 493 late in the month. That actually is a storm that moved south from near the North Pole. And you can see past just to the west of Banks Island there, and that actually storm continued over towards northern Hudson Bay. So all kinds of interesting stuff with this new database, but this storm track is an important concept for the impacts at any one place. Now, another, as we've been talking about, that geography. That's, of course, not changing on any time scales that we care about. So the aspect where you're facing. Also, what is the nature of your ocean exposure for coastal areas and impacts from storms? So are you in a small bay, or are you open facing, facing the ocean? Or in Alaska, of course, we have the issue that, say, in the Kuskokwim Delta, and YK Delta, really, we have communities that actually are not on the coast, but they're on rivers, but the terrain is very low lying, only a few feet above the sea level. All of that is going to influence the kinds of impacts that any individual storms can bring. Nearby terrain, of course, is also a big factor. And what actually happens at any given area is also going to be influenced by the depth of the water near shore, or if for a more technical term, the near shore bathymetry, the topography of the ocean floor there can have a significant impact on wave heights and water levels. So, how do we assess changes in storminess, given we've got different perspectives on storms, what storms might mean. Well, we'll of course start from the simple ones. So, from the meteorology perspective, we're really looking storms equal low pressure systems. So that is comparatively easy to assess, especially now that we have the right database to do that. So, we can ask questions like, are the number of storms in any given region changing over time? Are the intensity of storms changing? And is there a change in the seasonality? Say, is there more storms in the summer than there used to be? Or are there a decreasing number of storms in the winter? Those are the kinds of questions that we can ask. And when we say changing, we also have to specify what's the time frame that we're interested in. The number of storms, like almost everything in the atmosphere, varies from year to year. Some falls are stormy, some falls are not stormy, however you define storminess. Um, so an example of putting all that information together is in the little graphic there. So I just actually just got this data processed this weekend. So you are the very first folks to see this. So this is in the kind of the Chukchi Sea north of Point Hope in the Beaufort Seas over to the Mackenzie Delta for summer storms. So this would be the northern Alaska coast on into the Mackenzie Delta in Canada. And so the bars there, this is just the number of storms that met a pressure criteria of 1,000 millibars. That's pretty weak. So there'll be a very small number of storms that were never that strong, but not very many. And you can see there's lots of year-to-year variability. There's 2 years there in the 1970s and 80s when there were no storms in the northern Chukchi and Beaufort Seas. The thicker black line is a trend estimate, and in this case, there is a modest trend towards increasing storminess in the Chukchi, northern Chukchi and Beaufort Seas over the last 56 years here. This goes up through this past summer. But you can see that there's a lot of variability. The main thing is there hasn't been any really low years now, just 2 storms there, most recently in 2013 there. Since then, there's been at least 3, and all but 1 year have had at least 4 storms. And you can see there's some very stormy summers as well, although those have occurred back pre-2000 as well. So these are the kinds of things that we can answer. So now I can say, is storminess increasing on the northern Alaska coast in summer? And we can say, well, we do have some evidence now that yes, storms are more frequent within this relatively large region. Storms are more frequent than they were back, say, in the later 20th century. But I cherry-picked this example, of course. In most areas, in most regions, the number of L's on the weather map at a given threshold, pressure threshold, is not changing. If we look at winter storms in this region, for instance, we would find that there's no trend towards more or less storms. Overall, in most areas around Alaska, in most months and seasons, there isn't a trend, but there are some. This is one. But what about assessing impacts in storminess, which is ultimately, unless you're a meteorologist, maybe the thing that we care most about. So this is the impacts perspective. And this has a very, very different answer. There is exactly no doubt that impacts from storms are increasing. This is a timeline from our Alaska's Changing Environment 2.0 that we published at the end of 2024. And this is just a highlight of high impact events. And every single dot on here, except the handful of severe ice jam flooding events, were the direct result of storms. Now, between 2019 and 2024, there were about twice the number of state-declared weather-related disasters as there was in the 5 years, 2014 to 2018. And of course, 2025 continued that high threshold trend of more impactful storms. And these storms contribute to the landslides in southeast Alaska, to the extreme rain and winter events, persistent storms in the summer causing erosion in northwest Alaska rivers, the very, very near record snowfall in Anchorage a few winters ago, all storm related, all high impacts, and then on up to the things like ex-Typhoon Merbok and ex-Typhoon Halong since 2022 with very high impacts, all storm related. So from the impacts perspective, storms are having a much, much stronger, more impacts than they used to, even though for most purposes, most seasons, most areas, the number of storms, the number of L's on a weather map don't show systematic change. So why would that be? How can we be having more impactful storms if the numbers aren't increasing? Well, storms, of course, don't occur in isolation. They occur with background environment. Some of these are part of the weather climate system. The graphic here shows the track of ex-Typhoon Halong in October, and the underlying color field here is the ocean surface temperature departure from the 30-year average during the week that Halong made the trek from southeast of Japan up through the eastern Bering Sea and then eventually into the Beaufort Sea. And you can see that map has got pretty much almost only red colors there, indicating significantly warmer than normal ocean temperatures. Now, that is really important for storms. Warmer oceans mean just by basic physics, that means there's going to be more evaporation into the atmosphere. So that means that storms will have more water to work with. We have brand new research results that suggest that ex-Typhoon Halong was more intense because of these warmer ocean temperatures. Warmer temperatures, more water vapor, there's more energy for the storm to work with. So even though the number of L's is not systematically changing, most places, most time, there's more energy in the system. Another big feature thing that's become really important for Alaska recently, this atmospheric rivers you may have heard of. Atmospheric rivers play a role in almost every fatal landslide in southeast Alaska, and these are narrow ribbons of high moisture, high warmth content air that comes from the subtropics northward. These are not confined to southeast Alaska and are implicated in many of the major flood events, even winter rain events in Alaska in recent years. Of course, for coastal communities in the northern Bering and farther north, the presence of sea ice or lack thereof is a major factor in whether on the impacts of a given storm, with sea ice coming later in the fall, which is the stormiest time of year across northwest Alaska. That lack of sea ice acting to act as a barrier to waves and water runup means that the season when you could get coastal flooding is increasing. And the other factor is that wind fetch, the distance the wind is blowing over open ocean water, is an important factor. If, for instance, I tell you that it's Labor Day and you're at Utqiagvik and the wind is blowing out of the west at 50 miles an hour, are you going to have coastal flooding? Well, if it's 1968 and the pack ice is only 15 miles offshore on Labor Day, that strong wind is blowing over just a very short area of open water, that's probably not going to produce coastal flooding. If, on the other hand, it's 2026 and the pack ice edge is 500 miles to the northwest, that kind of wind could very well produce coastal flooding because the area where that water is being plowed up is much greater than it would have been 60 years ago. Now, those are kind of some of the Earth ocean system, atmosphere ocean system that play a role, but some other issues are important too. So, pre-existing conditions. Got an atmospheric river bringing heavy rain to your area. Has it been dry? Are the rivers low? That's going to have one effect. If the ground is already saturated and rivers are running high and you get the same amount of precipitation, obviously the impacts can be very, very different. Some longer term land changes are also a big deal. The poster child here, of course, is the flooding in the Kuskokwim Delta here this past fall with Halong, an area that's just barely above sea level, thawing permafrost, widespread land subsidence. When you're only a few feet above sea level, every inch matters. Infrastructure changes also are important to impacts. Do you have infrastructure in areas that there wasn't 50 years ago? Is that infrastructure, was it robust 50 years ago, but now is aging? Those are all factors for that play into impacts. And of course, then there's the overall sea level rise, the ocean water levels coming up as land ice, glaciers, and the ice sheets melt, and that water runs off into the oceans, as well as just the expansion of the oceans just due to warming. At the moment, that thermal expansion of the oceans actually accounts for about half of the sea level rise. And then there's the random component as well. And this was a big deal with Halong, the timing of the highest storm surge, that push of water. Where does that fall relative to the tidal cycle? In the Kuskokwim Delta, there's quite a large tidal cycle, and unfortunately, the shove of water with Halong almost exactly coincided with high tide. If that would have exactly coincided with low tide that day, we would not be talking about Halong. There would not have been major flooding in the Kuskokwim Delta. And obviously, that's a random factor. It's also regionally dependent. Tidal factor is only a minor issue in the northern Bering Sea and north of the Bering Strait, where the tidal range in most places is measured in inches. It's really not a factor at all. So all of these things can influence what actually happens on the ground, the impacts in any given region or community. All of these are in play for every storm. Now, I would be remiss in this presentation if I didn't talk about this X thing. I've referred to X Typhoon Merbok, X Typhoon Halong. The X often gets left out in the media. What is this about? So, storms that extract energy from very warm ocean water, 80 degrees or warmer, and have winds at least 39 miles an hour, so they're gale force, they get named. There's 80 to 100 of these storms around the world every year. The vast majority of storms at mid and high latitudes do not get their energy primarily from water, but rather from horizontal energy differences. There's about 10 times that many storms compared to the warm water storms. And they historically haven't gotten named. Some private weather forecasting outfits in North America have started doing that. In Europe, some government entities do that too. There's no meteorology criteria, though, as far as I can see for that. They're entirely impacts. If some government or private entity thinks they're going to be impactful storms, they name them. But except in Europe, as I said, that's a private thing in North America. So all this X means is this is a storm that began as a warm water storm and has transitioned to an air temperature difference storm. Okay, why do you care? That sounds like meteorological minutia, right? Well, it actually is really important because as that transition occurs, the area with strong winds expands greatly. Hurricanes, typhoons are actually quite small. They are much smaller. Even the largest hurricane typhoon are much smaller than a typical Bering Sea or Gulf of Alaska storm. And as these transition from warm water to air temperature, that area of strong winds expands greatly. 3 to 5 times. You could probably find even larger examples. And that means from the coastal perspective that the area of ocean water now being impacted by those strong winds greatly expands. And so you have much more water volume being pushed up. Typhoons, hurricanes, they're intense right near their centers. Often the strongest winds, highest water push only extends out 30 to 70 miles from the center. Of course, with Merbach, we saw coastal flooding 500 miles to the east of the center at one point. So that this transition means it's a much bigger storm, has the potential to impact much larger area. Now, since 1970, there's actually been more than 60 X-typhoons have directly impacted some part of Alaska. So Alaska is not new to X-typhoons. However, the vast majority, well, not the vast majority, let's just say the majority of those X-typhoons since 1970, so that's about one a year, has impacted the central or western Aleutians only. So basically, let's say ADCA westward. Now, less frequently, but not terribly infrequently, one of these X-typhoons will impact the eastern Aleutians, the Pribilofs. X-typhoon Ivy in October 1977 for a long time was the strongest, the lowest pressure storm on record in Alaska. That's since been exceeded here in the last decade. Even more rarely now, we have X-typhoons that work into the Alaska Peninsula, Bristol Bay, and very unusually, but it has happened, we have these storms actually make it as X-typhoons into the Gulf of Alaska as well. So that's the numbers there, kind of the frequency, the order frequency. Now, since 1970, which I think is about the limit of when there's good X-typhoon tracking data. Before 1970, there's no satellite data to feed into this, so it gets harder to track. So since 1970, only 4 X-typhoons have moved from the North Pacific through the Bering Sea and into the Arctic. The Arctic here being defined as north of the Bering Strait. Only 4. And as you can see from that list, 3 of them have been in the last 4 years. Between 1970 and 2001, only X-typhoon Carlo in October 1996 made that trek. Since then, there have been 3. X-Amphil in August 2024. That did not produce coastal flooding in Alaska, although it did produce some of the strongest summer winds on record on the Alaska northern Bering Sea coast. Now, the last 4 years, all occurring while since 1990, there's been a significant trend downward in the number of West Pacific typhoons. So it's not like we have more storms, so there's a better chance of this happening. Now, is it possible that we just have a run of bad luck here with 3 X-typhoons moving into the Arctic in the last 4 years? Could it be random chance? Yes. Is it likely to be random chance? Of course not. 1 storm, 1970 to 2021, 3 storms, 2022 to 2025. That sounds like something we need to investigate because of the potential impacts, as we've seen from Alaska. And I do want to leave, these are just the direct impacts. X-typhoons can also impact Alaska, even if they never get close, by sending more high moisture content and very warm air into the state, even if the storm dissipates or stays far away from us. Now, I also want to stress nearly every big storm in Alaska coast, Gulf of Alaska, Bering Sea, Chukchi Sea, Beaufort Sea coast, are not ex-typhoons. This is just a list of Bering Sea storms since the mid 70s that had big impacts and were in no way ex-typhoons. North and west coast of Alaska are already very stormy regions, always have been. And so what we have with ex-typhoons is we've got one more ingredient in an already very, very stormy area of the world. Now, here's an example of this is a plot here. The graphic is strong storms in the Bering and southern Chukchi. So Bering Sea north of the Pribilofs and Chukchi Sea south of Point Ley. And this is the August to November period. So this is the time when historically coastal flooding is an issue. The little blue bars there are the four typhoons that we've talked about. Now, as you can see from this graphic, you don't need any statistics there to see there's no long-term trend. There's lots of year-to-year variability with 10 or more storms in some years and just one or two in others. And so the typhoons there are they add a little bit, but if you took the blue portion of those bars off, the graph would look the same. But that doesn't mean that they're not important. Ex-typhoons are not a major factor in the number of storms, but because ex-typhoons are coming from the tropics or subtropics, they are bringing a key ingredient for storms that feed on air temperature difference. They are bringing the warm air with them. Very different than a storm, say, that forms over the northern Gulf of Alaska. If there's enough of a temperature difference, it'll spin up. But ex-typhoons are predisposed to become strong storms. And it's worthwhile to mention that all four typhoons since 1970 that have made the trek, North Pacific, Bering Sea, Arctic, all of them produced significant weather. Carlo and Ampil were big wind producers. Murbach and Halong, of course, in addition to wind, produced coastal flooding. So it's not, even though the numbers are not adding a lot because of this predisposition to be strong, any systematic increase in the number of ex-typhoons impacting Alaska has a potential to be high impact. And last slide here. What's the future of storm prospects? Will there be more storms? That is to say, the meteorological perspective, L's on the weather map. The answer is probably, but that is going to, as we've already seen, be seasonally and regionally dependent. Most seasons, most regions, we aren't seeing an increase. And if there's going to be an increase, it's going to take a long time to develop. Now, will storms be more intense? Not always, but sometimes for sure, because of that extra energy in the ocean that is being incorporated or is potentially incorporated into these storms as they go through their development and intensification phase. Now, will these storms bring more extreme rain and snow? That's a no-brainer because it's already happening, right? There is exactly zero reason to think that won't continue. And will there be greater or more frequent impacts? Absolutely, yes. Again, it's already happening and it's going to continue into the future. So here are my summary here and just some resources that we have for you here at the Alaska Center for Climate Assessment and Preparedness. Our homepage is there. I can't stress enough we are already seeing, as most of you on the call already know, more impacts from storms. And just because the number of L's on the weather map is not systematically changing, the rest of the environment is, and hence we have these high impact storms. Ex-typhoons, not a big number, but they have a potential to bring big impacts. They don't all produce coastal flooding as we've seen, but they have the potential to be major storms anytime that happens. Now, in addition to those resources I listed here, we do have several webinars coming up here. One of our big programs here at Plum leads that. We do lots of webinars. Every month, I do a climate outlook webinar, review what's happened around Alaska and the outlook for the coming month and season. So that's every month. And then here coming up here, we have a couple that might be of interest. We're going to have a webinar on emergency alerts. You may get these, so tsunamis, severe weather, volcanic eruptions, anything that can get that alert going. We're going to have folks on from the state, from some boroughs, from broadcasters on what these emergency alerts actually mean. And then April 21st, we've got coming up our annual spring breakup, river breakup outlook, and I'll be on that with folks from the Alaska Pacific River Forecast Center to talk about how things are shaping up for a breakup on the big Alaska rivers. So that is what I have for you today. Thanks very much to Vicki for inviting me to talk to you today, and be happy to take any questions or comments.
Okay. Well, thank you, Rick. That was really informative, and it's very interesting to see that basically we aren't getting more storms, but there is some suggestions that storms may well be having more impact, which suggests they're possibly getting more intense. Is that a correct correlation there?
When we look at the filtering the number of storms by intensity, again, we don't see much change. If storms were systematically becoming more intense, we would expect to see the number of those strong storms, or storms going from weak to moderate or moderate to strong, and we overall don't really see that. Now, 56 years is not a long time in the wonderful world of climate, so we may not just have a long enough record. I really think it's the other environmental factors, particularly the warming oceans and that additional moisture and the additional energy in the system, that's really driving the increased impacts that we're seeing around the state.
All right. Well, thank you. If anybody, feel free to post a question in the chat or the Q&A, or if you want, you can raise your hand and I will unmute you, allow you to talk, to ask your question verbally. Anyone? Well, again, I'll say thank you to Rick while I give people a chance. Oh, there we go. Oops, allowed to talk. All right. Eric Voorhees, I have allowed you to talk.
I don't have a question. I was just going to let you know that the chat's disabled. So if anybody has a question, they'll have to raise their hand.
Really? I thought I had enabled that. That is.
On my end, it shows chat disabled.
Oh, okay. There we go. All right. I think I just fixed that. So everyone, that's odd because it's not you. The default should be everyone should be able to chat. Oh, it is working now. Okay. So my apologies for that. I did not realize that had gotten toggled off. Thank you, Eric, for pointing that out. Anyone have a question? Okay. All right. Oops. What causes, here's a question. What causes a storm to do a loop-de-loop?
Yeah, so that's a good question. So what happens is the winds aloft, the surface low pressure system basically gets trapped underneath the upper low pressure system. And remember, the steering winds, 15 to 30,000 feet, become aligned with the surface low. Typically, when the storm is developing and intensifying, the associated low pressure system aloft is going to be to the west of that low. But when they get vertically aligned, then you get things like these loop-de-loops. Typically also occur when that happens, the storm center typically weakens, but not often, not very much. So it's basically when the upper levels and the surface kind of get into positional sync that you can get things like those loop-de-loops.
All right. All right. Anyone? I'm wondering if state, federal, and other agencies involved in community relocation or transportation are incorporating the increasing impact in their planning. Do you know, have you heard anything on that score, Rick?
Well, we would certainly hope so. But I think the aftermath of along here is showing the difficulty of that, as we've seen at Quingillingock and Kipnuk, where communities are facing, do they want to keep going through these kind of flooding events as the land subsides and as these impacts increase at least in frequency, whereas at least some agencies are like, well, we're going to rebuild kind of thing in the same place.
Yeah, and I would say that the one thing on the transportation issues, one of the topics of conversation is around sunk costs, about at what point do you say you're no longer going to keep supporting something in the same place, versus, because it's a lot of money to move infrastructure from one location to another, that then that has an impact on things. And then you get it, there's so many different moving variables. I would think people, as they learn about it, need to incorporate it, but to the extent to which it's already being done, I have no idea.
Certainly for community planning purposes, this kind of thing needs to be a part of the process. And I think both Murbach and Halong have shown that we need to think beyond outside of the box, in the sense that that impacts not only could be, but at some point will be greater than there's any memory or experience of. The northern Kuskokwim Delta area is no stranger to coastal flooding. They go through it a lot, but this event was beyond anybody's memory. Some communities saying, we never heard anything like this, from our elders and what they were told when they were young. So really beyond really any experience or memory or story. And that, it's when it happens to any given community, we don't know, but it's going to happen again. We know for sure.
Right. So anyone else? All right. In that case, I'm going to stop the recording and thank Rick for coming and thank everybody for joining us.